this graph actually came out a little better than I was expecting. One thing that isn't resolved is whether this graph comes to a point here and then descends, or whether it somehow comes up here and smooths out over the top and gradually curves over the top. It might be a fairly sharp curve, but at least is there a curve up here, or is there a point? And the same down here. So we can say, is this a curve or a point? The derivative function can tell us a little bit about what's going on here, and let me, before I talk about that, correct an error from before. This is cosine of omega t and sine of omega t, so the one revolution is in 2 pi, delta t equals 2 pi over omega, not just 2 pi. Again, that's something I expect that you understand at this point, and hopefully you picked up on that before. Okay, well, let's think about, first of all, this ellipse. Where are we in this ellipse at different values of t? Well, it should be clear that when t equals 0, we're here. Because when t equals 0, x is 1, y is sine of 0 is 0. And when t equals 1/4 of this 2 pi over omega, that is pi over 2 omega, quarter of the way around the circle, quarter of the time, that's not a circle, quarter of the way around the ellipse in the sense of, well, in no sense. Okay, when we're quarter of the way around the ellipse, the sine is going to be 1, putting us at the point 0, 2. The cosine is going to be 0. And then similar points here. When we're halfway through this cycle, we'll be here. 3/4 of the way through the cycle, we'll be here. And we could write out the expressions for those points. The thing I want you to see is if we're halfway in time between here and here, what does that do? Where does that put us? Where does that put us on this ellipse? Let's go ahead and look at the ellipse. Okay? If we're halfway between this point and this point, that means that the phase of the cosine is going to be 45 degrees, or pi over 4 radians, and the cosine is going to be equal to the sine. If you don't understand that, you probably want to think about it a little bit. But halfway in time between here and here, the y-coordinate, the sine is going to be equal to the cosine, so the y-coordinate is going to be twice as big as the x-coordinate, which means that we move from here to a point that's past the 45-degree point on the graph, where y is twice as big as x. Now, if we were to draw the line y equals 2x, have a slope of 2, that would put us about here. That means we go from here to here in the same time it takes us to go from here to here. And if you think about it, and again, you should be able to work this out, that means in an equal time we'll be over here, then we'll be down here, then down here, then here, here, and back here. So equal times, here, 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 here. Moving faster between here and here, moving slower here, but never stopping. Our t keeps changing, so our sines and cosines keep changing. So we kind of sweep this thing out faster and then slower, then faster, then slower, and so forth. That's going to be relevant because we're going to talk about this a little bit intuitively. Okay, let's see what our derivative of f with respect to t tells us. What is the derivative of f with respect to t, and why did I even talk about the time going around this ellipse? Well, between, actually, let's go ahead and mark off the equal time intervals. Okay, so we're taking equal time to get from here to here, and then same time to get from here to here, and then here back to here, and so forth. Just looking at the motion between here and here, we're moving faster here than we are here. df dt tells us how fast we're rising. So we're moving fast along the ellipse here, but what's our point on the curve doing? Well, the curve isn't as steep here, so even though we're moving faster, we're probably rising more slowly between here and here than we are between here and here. df dt tells us how quickly we're rising in time. So we're riding around this thing. We're going from here to here, then from here to here, here back down to here, here to here, and so forth, in equal time intervals. This expression for df dt. Out in front we have a 2 omega. Well, that's just a constant. The big thing we want to look at is this cosine of omega t times sine of omega t. This factor, cosine of omega t sine of omega t, is going to be 0 whenever the cosine of omega t is 0 or the sine of omega t is 0. And that means there are going to be instances where we simply stop rising or falling. At the x equal or t equals 0 point, the sine of omega t is 0. At this point of the ellipse, we're at this point because the cosine of omega t, which gives us our x of t, is 0. At this point, our y is again 0 because the sine of omega t is 0. And at this point again, the cosine of omega t is 0. So at this point of the curve and the point directly above the y-axis, the point directly above the x-axis along the minor axis, and the point along the major axis on the curve, we're going to have 0 derivative, which means that an object traveling along in time is going to not be rising or falling at this point, this point, this point, or this point. As we approach this point, our y value on the ellipse is going to be close to 1. It's going to be close to 2, close to its maximum value. Now, it's not going to change much from its maximum value near the peak of this ellipse, which means that the sine of omega t is going to stay pretty close to 1, which means that this part of our derivative is going to stay pretty close to 11. The sine stays close to 1, so 12 times the sine stays close to 12. Adding the negative 1, we get 11. The number 11 doesn't matter that much right now, trying to determine whether this is a curve or a point. The fact that it's nearly constant does. So we have something here that in the neighborhood of this point remains nearly constant and can be multiplied by 2 omega to get just another constant. So we have a constant times the cosine of omega t times the sine of omega t. The sine of omega t, as we've just observed, is staying pretty close to 1 in the neighborhood of this point. So really, we're just looking at how the cosine of omega t changes, and the cosine of omega t changes very smoothly. In the neighborhood of a point where the sine of omega t is close to 1, the cosine of omega t is going to be close to 0. And it's also going to be going from positive to negative. As the sine reaches 1 and then starts decreasing again slightly, the cosine is going to go from positive to negative. All of this tells us intuitively then that the cosine of omega t, which is nicely behaved, has very smooth behavior, is what really dominates the behavior of this function in the neighborhood of this point of the curve, and that we therefore expect that the curve is going to have a nice smooth peak here. It might be peaking rather quickly, but it's going to be smooth. One thing that disturbs me just a little bit about this expression is that when the sine of omega t is plus 1/12, which is going to happen somewhere pretty close to the x-axis or to the xz plane, but not exactly on the xz plane, when the sine is equal to 1/12, the negative 1 plus the 1 that we would get from 12 times 1/12 is going to be 0, so that there's apparently a point not too far from the xz plane and to the right of the xz plane where this curve stops rising for an instant. And I'm having a little bit of trouble seeing that in terms of this picture. So I'll kind of leave that as an open question. That leads me to suspect that maybe I've got an error in the calculation of df dt. That's a pretty straightforward calculation, and when we do our y squared, we clearly get a sine squared, and that's multiplied by a cosine, so that the sine cosine is going to be common to both terms, and we're going to have this factor here. So I really don't see any error in the general behavior of this derivative. I just can't reconcile it with the picture of the function. So I'll leave that as kind of an open question.